In this question, we have suppose the formation of nitrile fluoride proceeds by the following mechanism. We have step 1 and step 2. It says, suppose also K1 is much, much greater than K2. That is, the second step is the first step is much faster than the second. So in this case, the second step of the mechanism is this slow step. It says, write the balanced chemical equation for the overall chemical reaction. And in several other videos on this playlist, or at least a couple, we've gone over how to do this. So you add all the reactants together, you add all the products together, and you cross out like terms, and that gives you the overall reaction. So I'm not going to talk about that here. Here, I want to spend some time talking about write the experimentally observable rate law for this reaction. Well, since this case, the second step is the slow step, there's another example on this playlist where the first step is the slow step. And if you haven't seen that example, I would suggest taking a look at that one first. Here, we have the second step being the slow step. So, rate equals K2, because it's the second reaction, and it's the forward reaction, so it's plus 2, not minus 2, times concentration F, concentration NO2, is going to be the rate law for this reaction. And this is great because this is the slow step and this effectively describes the rate of the reaction. The problem with this is it contains an intermediate. You'll notice that F is not in the overall reaction. So therefore, it's not good for that to be in the rate law. And the reason for this is a little bit complicated, but we'll essentially just say here that it's really difficult to measure the concentration of F. Right? It's not like this concentration or this concentration or this concentration are relatively easy to measure. This is difficult to measure, so we don't want it in the rate law, so we have to get rid of it. So the question becomes, well, how do we get rid of it? And if you look at the previous question in this playlist, that's actually showing you how we're going to get rid of it. Let's look at this reaction, the first step of the reaction, and see how we can solve for the concentration of F. If we can solve for the concentration of F, we can then plug it into this equation and essentially get rid of it. Well, to do that, we need to think about this reaction at equilibrium. And when we do that, we think of the rate of the forward reaction equals K1 times the concentration of NO2 times the concentration of F2. So this is the forward reaction up here. This is an elementary reaction, so these are both 1 because the stoichiometric coefficients are 1. In the second step, we can look at these two products and we can think about the reverse reaction. Rate equals K to the minus 1, concentration of NO2F, concentration of F. So now we have the forward and the first reverse reactions. And let's assume for a second that this reaction is at equilibrium. So this rate and this rate are equal. And at equilibrium, K1, concentration NO2, concentration F2, equals K minus 1, concentration NO2, F, concentration F. So these two concentrations at equilibrium are equal. We can now, at equilibrium, solve for this concentration. Divide by K minus 1 concentration, divide by K minus 1 concentration NO2F. Cancels out on this side, divide this by K minus 1 concentration NO2F. And what we find is the concentration of F is equal to K1, concentration NO2, concentration F2, over K minus 1, concentration NO2F. So now we've solved for this. And since this is the fast step, this will reach equilibrium very quickly, and therefore this slower step, we can then plug in this information here because this is the slower step of the reaction. So now we have a value of concentration of F, we just found it, that we can plug into this equation, and now we have only chemicals that are actually found in the overall reaction. We don't have any more intermediates. So here the rate equals K2 times this thing for concentration of F, which is K1 over K minus 1. We can do it this way. Concentration NO2, concentration F2 over concentration NO2F, all times the concentration of NO2. So all I did was I simply plugged in for concentration F this entire expression. Now I want to simplify this. Rate equals K2 K1 over K minus 1 times NO2, there's two of them, we have to multiply them together, concentration NO2 squared, concentration F2, divided by concentration NO2F. If we have constants multiplied and divided by each other, it doesn't matter. You just get a new constant. To simplify, rate equals K, concentration NO2 squared, concentration F2 divided by concentration of NO2F. Notice, in this way, we have gotten rid of the F in the equilibrium expression. Note that this looks more complicated, so you might say, well, why would you use this more complicated one? Well, the reason is we can't measure the concentration of F. So therefore, we need to have this rate law so we can actually measure these values if we want to study this reaction. So this is the answer to this one. As far as what is K equal to, well, in the next one it says express the rate constant K for the overall chemical reaction in terms of K1, K2, and if necessary, the rate constants K minus 1 and K minus 2. Well, this is what K is equal to. It's K2, K1 over K minus 1. So that gives us the rate constant expression. So the good news is, even though this is quite a lot of work, it does solve both the problems when you do it.